Okay. I think it's recording now, right?
No, because it doesn't show me.
Oh, let's see. Um, okay. All right. So yeah, so here's my poster. This is my project. Thank you. Any questions?
Are you recording?
I think so, yeah.
No, because it doesn't show me like the consent. I have to press like, yeah.
Oh, maybe I didn't.
If you record, I have to accept that.
Oh, that's weird. It shows that I'm recording because it shows that it's recording on this computer.
Oh, it's weird. Okay, yeah, no problem. Continue. Sorry.
Okay, so yeah, so my project deals with the synthesis of chiral monomers derived from vinyl and their characterizations using spectroscopic and analytical techniques. Uh, my research here was all with Dr. Joe's. I it does show that like I was doing research also with Dr. Benavides. However, I didn't get to do that part yet, so I'll probably do that in maybe the next following weeks, where I just characterize and like model the compound that I obtained. Um, but yeah, so basically, what I did was I initially the um, the monomer that I started off with is a compound um, that other students had synthesized here previously at the university, and the steps that I followed were from literature that Dr. Jost provided to me. After like reading it, like I just had to like come up with the steps in order to like finish off this monomer. So uh, there's only 5 steps in my research. However, um, I didn't get past step 1 just because of like how hard the synthesis was. Also, there was a couple of complications throughout like this step that I just had to like I guess figure out how to move past with the help of Dr. Jokes. And so basically, we'll start off with the vinyl, and then afterwards react it through an SN2 reaction via the Williamson ether, uh, just a regular Williamson ether reaction or synthesis. I'm sorry. And so basically, the next step after that would be bromination to brominate the compound. But so since mine only, since I only got through step 1, basically what I did was I started off with my vinyl compound. The literature did require us to use 1-bromohexane. However, that wasn't like readily available to us, and so we decided to use another alkyl halide. Dr. Joe suggested that we use any alkyl halide that was in lower than 6 carbons, just because of the bromohexane being 6 carbons, right? So we had the iodoethane or the methyl iodide in the lab, and based off of like theory and stuff that we've learned in class, we were like he mentioned that the reaction would proceed a lot faster with us having it with the halide being iodine instead of bromine, and therefore after I mixed the vinyl with my iodoethane, the sodium hydroxide, and my solvent, which in this case was hexane, not hexane, sorry, acetone. Acetone, the literature called for me to like place it in a reflux condenser. However, the reflux condenser here was really hard to work with because as you can tell, it's digitally run. So here I would have to change the temperature. Initially, the temperature that we set it to was the boiling point of our acetone. However, the flask wasn't condensing. And so I just had to like play with this digital meter like until the glass eventually condensed because that was part of like, you know, what needed to what would help the reaction move forward, right? And instead of just like stirring for a constant amount of time. The literature itself did also call for like 18 hours of you know, constant stirring and heat. However, while I was monitoring it like through TLC, like I didn't notice a lot of the product being formed, which is at that point I informed Dr. Joe's and like we let it run for about like maybe 3 4 days before we decided to like, you know, after those 3 4 days the same results came back, and at each point I also had to add more of the methyl iodide, but it still wasn't creating enough of the product that we wanted. So after that week, the following week, he had me like place it in the rotary evaporator to remove all the solvent and basically start from step one. The What we noticed in this flask over here was that it was turning yellow, indicating in a way that it was also some of the iodine, right? So some of the methyl iodide was also evaporating, which was interesting because I mean maybe the temperature was on too high or the flask was too small. So one of those, right? However, in the end, I guess we just ended up with like a really like viscous solid, which we thought to be the original vinyl, just in like, you know, like in this like liquidish form. So after that, I pretty much started like, you know, doing the same steps all over again, adding my acetone with my iodoethane and the sodium hydroxide solution, which I made in the lab. It was just, I think, a 1 molar sodium hydroxide solution. Then afterwards, after, you know, figuring out how this condenser worked, like things got tricky because it would eventually start like condensing. However, at certain points, like the next day I would come and it stopped like condensing. So I'm like, what's going on? And I would have to like, you know, change the temperature and then it worked, but then it would stop and then it worked and it stopped. So that was really, really, you know, like confusing. And I'm like, what do I do? Eventually, like, you know, through TLC, I did see that like enough of the product was being formed. It was really cool because the bottom of the flask, you could see like an oily substance. Based off of the literature, the product that we were supposed to obtain from step one was an oil. However, after I left it out in the like just here in these beakers, because I had to like decant it. After I did that, the oil turned into a solid, which was kind of interesting as well. Later on, Dr. Jones mentioned that, like, you know, it might have been because they used an alkyl halide with a longer chain than we did. And so, as you know, for them, the packing would be a lot harder, which would eventually lead to an oil. Where for us, it was just, you know, a smaller chain, which led to the solid forming. Because of the solid forming, I did have to, you know, eventually, like, you know, put it into another solvent so that I could do a TLC and see if that was like, you know, like the product that I wanted. And then after that, I had to, like, you know, completely dilute it to put it into an evaporator, not an evaporator, to a separatory funnel. In the separatory funnel, because I didn't know if there was any unreacted vinyl, I mixed it with a sodium hydroxide solution, 1 molar sodium hydroxide solution, in order for that to create, like, to react with the unreacted vinyl. And then after that, like, you know, creating the aqueous layer and the organic layer. The organic layer stayed on top, which was, you know, great because then we would be able to separate the two layers easily. After I did that, I went ahead and again used the rotary evaporator to remove any of the solvent that was still present before testing it out in like HNMR and IR. However, Dr. Jost did mention that like this probably wouldn't like remove all of the solvent. So the thing after we did this was to connect the flask with the use of a what is it? I think they're called adjusters, and then connect that to the vacuum to kind of like suck out like any of the remaining solvent. Just because after the I guess our solid would like completely solidify, like you could like through the little crevices, some of the solvent would be, you know, escaping, and through suction we would be able to remove it. So after we were like, okay, well, I think we're done. We then took it to HNMR and IR. Based off of the results that we obtained, we did see that like the product that we had was indeed the one that we wanted after for step one. However, we did see additional peaks that were not supposed to be there. We later spoke about that, and Dr. Jost concluded that it may be the peaks that were shown were probably because of the solvents that were still present, if not all the solvents were removed. And we're since we're continuing this project, we're just hoping that after we after the subsequent steps are worked, then these peaks will go away through these because I think we're gonna keep on doing some of the steps to remove the solvents. So we're hoping that that's the case after we test it again. Yeah, and after this, my next step is to use to brominate the solid that I obtained, and then three other steps pretty much. So I'm kind of looking forward to for a final monomer, because after we obtain the final monomer, then we get to mix it with another one and form the polymer that Dr. Jost is looking for. Well, yeah, that's basically it. Any?
I have a question for you, Older. This is Maria Benavides.
Oh, hi, Dr.
I know, I mean, from what I was able to listen to you, that you've been working on synthesizing these monomers, right?
Yes.
And there's going to be more than one, right?
So not more than one. So it's just one that we're kind of working with along the 5 steps.
Okay. Well, I mean, I thought you said that you're later on you're going to work on another one, but it's the same. Then
Yes.
it's on. Okay. No, because I was curious. I mean, if you had more than one monomer, if you were considering then to start creating the polymer and maybe using multiple monomers or just the same monomer.
Oh, well, I know that based off what Dr. Jost has mentioned, that since it is a racemic mixture that we're working with, I think there is one specific, I'm not entirely sure if he wants to work with the R or the S.
Okay.
And based, so I'll have to ask him and see which one he wants to work with.
Yeah, because it will give you different results because they're two different isomers.
Mm-hmm.
Yeah, but how can you separate them if you have the racemic mixture? What do you know? What would be the procedure to separate those two?
I'm not entirely sure, but I know he's mentioned it before slightly. I think, yeah, so I would have to ask him again on that one.
Yeah, what separation technique will need to be used, right?
Mm-hmm.
Okay. Yeah, sounds interesting.
Yes, I've enjoyed it.
How big is your monomer? Can I see it?
So
Let's see. Can I look at the structure?
yeah, so this is from the literature, but like
but which one is, what is it that you're trying to obtain? What's
Oh,
your end product?
So it is this one. However, there's an additional carbon chain, carbon here. So instead of this just being one, we have another. So another carbon. So
Okay.
a methyl instead of this ethyl.
Interesting. And then once that this is produced, and I know I came late to your presentation, if this is a monomer, okay, and I can see that your nitrogens have plus, or all of that has an orbital +2 charge, or what?
Oh,
Because you have 3 ethyl groups, right? Plus is connected to that other branch there. So do you have an orbital charge that is +2 there?
I'm not entirely sure about that one, Dr. B.
Because notice that you have, before that you had nitrogen 2, and then you're moving into having 3 ethyl groups connected to that, to each of those 2 nitrogens. So now you have 4 groups connected to the nitrogen. So that means that a pair of electrons move to form a coordination bond with one of those ethyl groups or the chain. So you have now a +2 orbital charge. So what will be your counter ion in this case for that 2+ charge?
I guess
you can ask Dr. Jones, because you see, before that, the previous step, you have those amino groups there, right?
Yes.
And that's fine. It's nitrogen with 2 hydrogens, and then it's connected to that ring, right? But then when you go over here, not only that, you have, it's no longer the amino group directly connected to the ring. Now you have in between a chain, right?
Yes.
And not only that, you have, in addition to that nitrogen being connected to that chain and no longer directly connected to the ring, you have 3 ethyl groups connected to that nitrogen. So now there's 4 groups connected to the nitrogen instead of having just 2. And therefore, in your notation, you have a plus and plus charge on each of those nitrogens, because now they have, they have a valency of 4. You see that? What you have? I'm just curious. I'm just looking at it.
Hello?
Yeah, your cursor is a little move. Yeah, you're close. I mean, your end product, what you have there, that's a 1.
Okay.
That,
Sorry, I think it cut off, so I couldn't hear, like for the last couple, for the last minute or so, I couldn't understand or hear.
okay, what I'm saying is, number 1 is your product, right? That's what you're trying to obtain, right?
Yes.
And what I was saying is, in each of those nitrogens, because you have 4 groups connected to it, they have a plus charge, right? So overall, there's a 2+ charge.
Yes.
But you cannot have just a compound with 2 positive charges, because you have to have charge neutrality. So there has to be something else that it functions as a counter ion that has a negative charge to counteract that or counterbalance that, those positive charges. Do you know what that is, or you don't know what it is?
No, I don't know what that is yet.
Yeah, I'm curious. I mean, what that is, because of the way that it looks like. And it's also interesting to see that those nitrogens are no longer connected directly to the rings.
Yes.
So how do you go from those amino groups into those nitrogens no longer connected to the rings? There must be steps in between, I suspect.
Yeah, so the next step that I would do would be bromination, and then after the bromination, I need to do
So, and at what stage are you right now? I see 1, 2, 3, 4, 5 steps.
Yes, so I was only able to go from 2 to 3.
Okay.
Yeah, and so my next step is the bromination of 3 to 4. And then from that, the double cyanation.
I can see that in the next one.
And
then you reduce it, right?
Yes, the reduction of the protective.
But what happens to the carbon that is there? You have a nitrogen with a triple bond to a carbon. That carbon is connected to the ring. What happens to that carbon?
Oh, I think this one is based on there is other there is another like article that Dr. Joe sent me where he deals with this one here.
Yeah, because I mean, you cannot just go directly, and then once that you have your amino group directly connected to the rank, notice that when you go from between 4 and 5, you have now amino groups, right, connected to the rank. But then when you move to the last product that you have there, now that nitrogen is no longer connected directly to the rank, it's connected to a carbon.
Oh, so,
So how do you go from, I mean, step 5, what takes place there? There must be multi steps there.
I'll have to double check with him, Dr. V, on this one because I remember
There's more to it. I can tell you by just by looking at it, there's more to it. You don't just go directly through step 5. There must be multi steps there. And I'm just curious as to what they are. But based on what you're describing, you're right now in a structure 3, right?
Yes.
That's where you are right now.
Mhm.
Okay. Interesting.
Yeah, it's been fun. I've been,
Yeah.
I was telling Rafa that like I was kind of scared to go into the lab at first because it's the first wet lab
What?
that I
Why is that?
Well, because all my labs for organic were online, so I didn't know how to use anything in the lab.
Okay. Now I can see you have another person here, Nat. I don't know if you want to give them the presentation, but thank you for answering all my questions, Older. I mean, this is a good project, very interesting.
Yeah, thank you for the questions, Dr. Reed, because I mean, they're definitely gonna, kind of help me move forward and like do a little bit more research on like what you asked.
No, this is nice. I mean, I like synthesis, and always coming up with new materials is very interesting, and I applaud you for that. Very good project.
Thank you.
I'll see you. I'm going to visit someone else now.
Okay.
Bye.
Bye.
Hi, Elder. Good job.
Thank you. Rafa.
Bye.
Bye.
Bye. Okay, so now is Nat. How are you, Nat?
Very, very well. How are you?
I'm fine. I was just listening and asking questions to Older. I mean, but I'm gonna step out now so that he can talk to you from the beginning.
Oh, it's okay though. So you actually work with him on this project or?
Well, I mean, this is actually up to this point where he's including here, right? Older, this is where you're done with Dr. Joe's. Are you already modeling this? I mean, Older, because I noticed that you already started working in the computer, right?
Yes, yeah, that's my I wasn't able to put it on here, but like I was going to check the IR through the modeling for
That would be great because this is ideal. You have an NMR, not just an NMR, you have an infrared spectrum and actually very well resolved. You have a lot of peaks there. Although ideally, you don't want to have any of the impurities that you mentioned. If you still have solvents, then it's going to confuse you. You're going to say, where is this peak coming from? So it would be better to have a more clean infrared spectrum. But that once that you have it, and if you model these compounds, and if it's the same compound, they should match very well.
Yeah.
Plus, you'll learn a little more about these compounds, not only the synthesis and the characterization, but then you can model it and then try to explain your characterization as well. So it's going to be pretty cool.
Yeah, and that's what I'm gonna be doing this next week. Just trying to finish that so that I have that information at each step.
Yeah, and I need to check it. I mean, which one is the one that you're modeling? And it's a good question that Nat asked that. Are you modeling number 3 right now? Because that's where where you are at this point.
Yeah, I would model number 3 now. However, right now this chain is just from the ethyl iodide. Here I guess they just like so it would look a little bit different.
And I would like to see it when you're doing it older because it might be tricky. You have those hexane chains next to the oxygen, right? They're connected to the oxygen. These are very long. Okay, so it might be tricky to optimize that area. Now,
but since so the literature initially called for 1 bromohexane, but like didn't have that in the lab. So instead of 1-bromohexane, we used the methyl iodide.
So, but I mean, that number 3 structure is the one that you have right now?
More or less, yes. I would
Yeah.
have.
Now, what I was trying to tell you is when you have this hexane change, because that's a hexane chain, right? It's 6 carbons. Then they might be a little bit tricky for you to optimize it because you have this 2 change and they have a lot of conformational motion.
Uh-huh.
So it's sometimes tricky to get it right to begin with. So you might struggle a little bit with the optimization. That's all I'm saying.
Oh no, yeah. So I understand that, but I don't think I'm gonna have a hexane chain.
Oh,
Yeah, just
because that's what it's showing here. What are you
Okay.
going to have instead of the hexane chain?
just a methyl. Yeah.
And methyl. Oh, those are very easy. Very easy to mount. Oh, here is Vishwa. How are you, Vishwa?
I'm good. How are you?
Fine. Asking questions to all the right. Just before Nat joined in and then before you, I was asking a lot of questions to Older.
Good question. The whole PChem class is gonna show up right.
Yeah. But anyway, I'll let you go, Older. We'll talk about it, okay? So that I can see what you're doing.
Okay, thank you, Dr. Ree.
And it's good to see you, Nat, and good to see you, Vishwa.
Yeah, bye, Dr. Benavides. Have a good day.
Bye. You too. Bye.
Hey,
Hi,
Vishwa.
Older. How's everything?
Good. Listen, y'all want to hear my presentation?
Why not? Show me what you got, bro.
I just winged it because I mean, I don't have a lot to present, right? So it's just like, because again, it's just going through like the one step, but basically it's like the synthesis of like, my synthesis, like you saw here, deals
Uh-huh.
with like 5 steps, right?
Yeah.
Uh, I think from whenever Dr. Joes was showing me this, he noticed that there's here there's only 1 carbon, but here there's like there's this carbon here. There's a change, right? And he was like, maybe they made an error there. So I'm gonna have to
So,
ask him again. But
so how do you think like, cause I can see from here you have the C and triple bond, right? So
yeah,
I think there will be the like maybe like the type like a typo on the 6 substance. So I think that will be some sort of like a methyl group or like yeah, something like that linked to the nitrogen, not just the carbon like evaporate, like just completely disappeared over here though.
yeah.
So I think what the step is gonna do, like reducing the triple bond into the single bond, and you will have the 2 hydrogen connecting to the nitrogens over here.
Mhm.
So I think you need to double check the structure of the 6 step that you were doing.
Yeah, I'll have to, now that everybody's bringing it up, I think that, I do remember him saying that there was a typo, because I asked him about it too, and he was like, oh yeah, I think that that's just a typo. So,
Yeah.
but since but now I'm just gonna have to keep that in mind. Good thing that it's recording because
Yeah.
I can go back to the recording and see. But yeah, no, so basically, I only went from like 2 to 3. From 3 to 4, like you can see, we'll have to do bromination next.
Bromination.
Uh,
Yeah.
and then after, from 4 to 5, we do double cyanation.
Like
Uh,
how you gonna move on the bromination to the double like cyanation?
oh, that's a good question. I haven't really looked into that yet, just because I'm like kind of looking into, like, I have the steps and all,
Uh-huh.
but I haven't really gone through them in depth, just because I'm like, okay, well now I'm just gonna go from 3 to 4, so I'm like
Yeah.
more focusing on the bromination step now.
Mm-hmm.
Yeah. So
Yeah.
yeah, whenever
Then
I
I
get
think
to that, I'll let you know and laugh. I'll be like, oh.
yeah. Then I think the next step will just like breaking the triple bond into a single bond, and you will have some hydrogen as attacking to the nitrogen. And then on the next step, like probably just prop like protonation the nitrogen, getting some ethyl attracting to the nitrogen. I think that's the purpose of the lab could be.
Yeah. Yeah, because from 5 to 6, we do a reduction, right? And then here we're using THF and then
The tetrahydrofuran.
yeah, um, and also lithium aluminum hydride. And so for that step, based off of the steps that I have in front of me right now, what we're also gonna do, we're gonna degas the solution with nitrogen and add dinitrile solution to the lithium aluminum hydrate solution. Yeah, it's a long process because I'm like, oh, I thought it was only 3 steps, but it's like 7. Yeah, it's a long process.
Have you done any analysis on your system?
Yeah, I just did HNMR and IR, but based off what I got, like these
Ooh,
are
that's like a loss of peak for the IR though. Like you
yeah,
have like
yeah, they there's a lot of peaks, so
yeah, I can see some sort of like a weak peak of the. It's look more like the amino than the alcohol peak, is it? Or is this the alcohol peak?
that's the alcohol peak. I think.
The alcohol?
Yeah.
Yeah.
But with the
So
HNMR, like we did see like certain peaks that were not supposed to be there, but like the smaller ones, because of like Dr. Jones was saying that like it was mostly probably the solvent that was still present.
yeah.
And so he was telling me that like as we keep on moving forward with like with the other steps, like eventually like those peaks will go away. So so as far as like everything that we've done, like based off of like HNMR and IR, like the product that I have is the correct one. However, it was weird that like in the literature said that we were gonna get an oil, but
Yeah.
I don't know if you've seen the flask in the lab, but it's a solid now.
It's a solid right now?
Yeah, so it's a
Like
solid.
the solution like completely evaporate?
No. We evaporated the solvent.
Like you using the rotary evaporator?
Yeah, by using the
Oh
rotary
yeah.
evaporator. And then afterwards, but like the literature that he had me read says that our product for step 1 is supposed to be an oil, but for me, after I left it out, like it turned into a solid. Yeah.
Kind of interesting though. So you take the IR of that solid?
Yeah, so we had to like dilute the, well, not dilute, but we had to dissolve the solvent in, I believe, well, one of them was chloroform for the
For the
HMR.
carbonated.
Yeah, and for the for TLC to test it out with TLC, I think we used dichloromethane. So, but for the other one, the IR, it was just like we didn't have to turn it back into a liquid because you've used it, right? You just turn in the little solid.
The Leo solid?
Yeah, like you just put a little spot of like the compound in the IR
On the
machine.
TLC?
No, no,
On
no.
the IR machine?
Yeah.
Oh yeah. Just a little small pot like in the center so you'll be able to take the IR.
Yeah.
But
Yeah.
like before you take the IR, like you need to clean the needle and also the surface, like not to get any contaminated, right?
Yeah.
Yeah. So
I need more practice with those.
yeah, we'll see. Will you continue on the summer or like fall semester?
Yeah, yeah. I already asked him if I can continue it in the summer. He's gonna be here in summer 1, but not summer 2. But then I'll continue it in the fall, just so that I can like try to finish up the project. Because it'd be kind of cool to see how like the final polymer.
Yeah.
Yeah.
I saw you still have a lot more step to do though.
Yeah.
Good luck on that.
We'll see how far I get along. If not, like some other student is gonna continue it.
Yeah. All right. Thank you so much.
Yeah. Thanks,
All right.
man.
Yeah. See you then. Bye.
Hey, Victor.
Hello.
How are you?
I'm good.
Any questions? I know it's already past our time, right?
Yeah.
Oh, we have to go back to the thing, right?
Really? I thought it was you guys had an hour.
Yeah, we have to go back to closing ceremony.
Oh,
Uh,
like
wait, you're not in you're in SA, right?
no, no,
Oh,
I'm
well,
not.
yeah, well, I have to go back to the
Okay.
ceremonies. Okay. All right, bye.
Bye.
Thank you for stopping by.
Bye. All right.